In the first list or program for this semester, the title of my presentation was Process Mineralogy of Industrial Minerals. I decided to change that in the last minute because I wanted to include the aggregate production. And that's the last project I started working on. I'll tell you a little bit about that during this presentation. As Susanne said, I'm from NTNU, Norwegian University of Science and Technology, from Trondheim in Norway. My education is completely from NTNU, master and PhD from NTNU. I have a resource geology degree, working a little bit as an exploration geologist, and then moving on to my PhD in working in quartz, which is more like mineralogical interprocess mineralogy, and then moved on to work in the industry with quartz for a company called Aggregate, that is one of the major silicon producers. And then in 2012 I moved back to the university and started working as an associate professor. Short agenda for the day. I'm going to say a short background about NTNU and myself. Say a little bit about why I've chosen to call it non-metallic mineral deposits. And then short about process mineralogy before I go into the examples of application of process mineralogy in these sectors. First, where is NTNU? Well, this is a world map, as you probably recognize. We are now here. Norway is quite far north, quite different from Brisbane, of course. Trondheim is in the middle of the country, more or less. NTNU is recently expanded to not only be located in Trondheim, but also in the small towns Ålesund and Gjøvik. The capital of Oslo is just have to see what I was supposed to say here. NTNU, short facts: 9 faculties, 55 departments. The budget is about $1.5 billion Australian dollars, last in 2018. We have constantly more than 40,000 students divided onto these 3 campuses, more than 30,000 in Trondheim, a city which is just 200,000 people total. NTNU has a close cooperation with industry and SINTEF, which is a major independent research organization, started up from NTNU, but then working independently. And 396 doctoral students were graduated from NTNU in 2018. I represent the Department of Geoscience and Petroleum and a research group called Mineral Production and HSE or HSE, Health, Safety and Environment. This mineral research group, we do research and education in the entire value chain of mining. So from geology, research geology, mining, mineral processing, and environmental effects from mining. And together with the rest of the department, with more geologists, engineering geology, it's a complete value chain. We have projects related to national and EU funding. So in geometallurgy, deep sea mining, flotation, fine particle processing, and those examples. And the department has extensive cooperation with industry, Norwegian mining industry. We have great laboratory facilities, which are growing, which is the example exemplified by what Susanne said, that we are developing this EM laboratory with EPMA automated mineralogy. The staff at the research group is now 5 full-time researchers and staff, scientific staff, representing resource geology, or technical resource geology as they like to call it, comminution, flotation, mineral processing, and process mineralogy. And we are expecting a mining engineer professor and mineral resource management professor to start during 2020. And we have a couple of adjunct professors and PhD students and postdocs, of course. And the laboratories we have are chemical mineralogical lab with analytical equipment for XRF, XRE, ICT. We have a very good, very good thin section lab, as we call it. So we have 2 full-time staff preparing thin sections and polished rocks for us, which is very good for our microscopy labs, electron microscopy, optical microscopy. So very well equipped. We have a mineral processing laboratory. We have been recently moving, so we have a brand new facility for mineral processing, just starting up this fall. So spring in Australia, fall in Norway. And geological engineering, rock mechanics laboratories, and rock magnetic laboratories. And then we also have national research infrastructures related to TEM, nano lab, X-ray facilities, etc. that the department can use. So laboratories are well served. Yeah. Coming over to why I decided to talk about, call it non-metallic deposits. You probably know about this, how you classify mineral resources. We talk about metallic ores, we talk about industrial minerals, we talk about extractive minerals, we talk about energy. Metallic ores are mined for their content of metals, as you know. Industrial minerals, they are mined for the mineral or several minerals and their properties, not their elemental content mostly. And extractive minerals are construction materials for roads, concrete, constructions, and dimension stones like granite, marbles and stuff for decorations and roofing. However, these classifications can vary. So the US and Australia has slightly different classifications within this. Norway has its own classification. So Australia, for example, as I read, classify rare earth elements as industrial minerals. It's separate from the government. Correct me if that's not wrong, but that's how I understood. In Norway, the Mineral Act says that any ore contains metals with specific gravity higher than 5 grams per cubic centimeters. Hence, that's also represented in the classification system. So they vary a little bit. But Norway has very few metallic ore deposits that we mine today. We have not very big mining industry. The production is around 100 million tons of ore per year. That includes extracted minerals, it includes industrial minerals and metallic ores. Sales value is about $2 million of all this. And 40% of this is exported, and most of the export is actually construction materials. So, Norwegian mining industry is dominated by extractive minerals. And this is the main, or the biggest quarry for extractive minerals. It's a granite diorite on the west coast, which produced mostly for export to the European continent and the UK. Well, I think it's about 10 million tons per year they produce, mostly for export. Just a very tiny amount of that goes to local use in the area. And there are several forests like that along the west coast, exporting to Europe that doesn't have qualities of aggregates that can be used for specific purposes. They mostly have sandstone, doesn't have the approved resistance to wear and tear. And then industrial minerals, represented by limestone quarry in the middle of Norway, which produces about 3.5, one of the largest industrial minerals mines, producing 3.5 million tons per year, approximately. 99% calcite. So limestone, quartz, feldspar, and feldspatite, olivine, that's the major industrial minerals. And industrial minerals is usually regarded as a low-cost material, low-priced. That's in Norway, which is a high-cost country for labor and production. Industrial mineral sector survives because we have specialized in high-tech, high specialty, high-purity products. So we spend a lot of effort on developing specific products from our industrial minerals. That's also where our mineralogical competence comes in, to contribute to guide the development in the industrial sector. And then metallic ores. This is an iron ore, Aggregate, the only real metallic ore mine in Norway, producing about 3.5 million tons as well, ore per year, and must feel a little bit alone. But we also have a ilmenite mine in the southern part, which can be related regarding the metallic ore if you use the ilmenite as ilmenite source. It's mostly used as a titanium oxide source, so in reality it's industry. But the future for metallic ores is bright. We have a sulfide deposit that is being developed currently, which is going to be probably Europe's largest copper mine. It has a indicated and inferred resource of about 66 million tons and 1.5 grams per ton, no, 1.5% copper. They have most of their approval accepted. They just need mining concession and are finishing their final feasibility study, as we speak. And hopefully within a couple of years they will be starting up. And that's one of the reasons I'm here, to learn, hopefully, to work with you and learn a little bit about sulfide mineralogy, sulfide process mineralogy. So that was Norway. So why process mineralogy? Why do I say I'm doing process mineralogy on non-metallic deposits? I think there's a general understanding that process mineralogy is all about metallic ores. It's about optimization of mineral processing of metallic ores. And that was how it started, for sure. But there are some recent definitions that's related more to any mineral commodity. So, for example, my old supervisor, Teddy Marvik, he says that process mineralogy is relates the physical, chemical, mineralogical, textural properties of mineral raw materials to their behavior in the process, to product quality and the utilization of the mineral products. That opens up for more than metallic ores, because it doesn't specify at all. And lately, the process mineralogy book that was published from here says that process mineralogy is the application of mineralogy in making processes more efficient and effective. So also it doesn't specify ores, and Elaine has to say if that's okay or if it should have been specified for us, but we can discuss that. But the important thing is that process mineralogy links mineralogical properties of a mineral raw material to the processes required to make a sellable product from an optimized process. That's how I see it. So for non-metallic ore deposits, you can easily see there's some differences from metallic ores. We don't often talk about grade that much. We don't talk about mineral liberation has another importance in this type of process. Some of them, for sure, there's mineral liberation is important, but maybe on different scale or different way. But the content of impurities. So rather than talking about grades, we talk about the content of impurities in the process. So you have to classify what type of impurities and how the impurities are situated in the minerals. So many of these deposits, they are naturally high purity, like quartz deposits and limestone deposits. They have to be around 98–99% of the main mineral, and the rest is impurities that needs to be accepted or removed. So I'll show you about that afterwards. In many cases, it's about upgrading lump-size material. We work with, well, the product is very large size, maybe 130 millimeters. That's a small size. But still, you need to link it to their behavior in the downstream processes. So in the silicon furnace, in the limestone kiln, when you prepare limestone, so understanding impurity distributions is important because you're not able to remove it in many cases. You need to accept it and mine to have reduced impurity. And also to know how to blend different areas. Mechanical strength, thermal strength may be of importance in many cases. And since you're working with lump size, producing lump size concentrates, you have to increase yield by reducing fine contents in the concentrate. So repeating a little bit, but feed and concentrate grade is not a topic. It's more the purity or element content in the concentrate. It might be color. If you're producing pigments, the color can maybe the main final quality parameter. For limestone, when you're producing limestone for as filler in paper, for example, they need a certain whiteness. If you have 0.25% sulfides in that, the whiteness is good. So you need to be able to work out how the sulfides is located if we want to alloy them or remove them. Okay. So then into some examples. This image, it's a fairly old image, it's said to be from 1998, but this part hasn't changed much. The mining is not into the mountain. This is a quartzite mine located far north in Norway, just 2 hours from the Russian border, and almost as far north as the North Cape. This wall, for geologists, this is a total view of formation called Gamma Sphere Formation, which is quartzite unit. It looks nice here. It's more purple if you see it as a hand specimen. And from this level and down to here, it's about 300 meters. Only the top, about 30 meters, is pure enough to be mined as a raw material for silicon production. That means purity higher than 98% quartz in Europe. And this is one of the raw materials I did my PhD on, so I decided to give the examples from my first work and from my latest work. So this is from my first work I did as a researcher, and then the second example with aggregates. That's the latest work started. So from quartz deposits you can produce two very high tech or high specialty products. We call them metallurgical grade quartz, which is quartz intended for silicon production and reduction in the furnace. And you can talk about high purity quartz, which is more upgraded by mineral processing, traditional mineral processing methods, to very high purity quartz. So silicon is produced and needs to be more than 99, up to 99.9% silicon. Whereas high purity quartz is about, the best product is 99.9998% SiO2 in the product. So in both cases, impurities in the quartz is very important. For high purity quartz, most of it is related to challenges with mineral processing. I'm not going to spend so much time on this. I'm going to spend most of my time here talking about how to characterize metallurgical grade quartz. And in the silicon furnace, thermal properties of the quartz, thermal strength or thermal resistance of the quartz is very important. The concentrate that's fed to this furnace is 130 millimeter size. So everything less than 30 millimeters is regarded fines. In some cases, they may add some controlled amount of 20 to 30 millimeter quartz as well. But mainly it's from 30 to 100 millimeters. And the yield from the mine is defined by how much of the quartz is produced as the silicon they produce from these furnaces is intended for chemical use and as a raw material to electronic grade, that is further refinement of the silicon, or it can be for solar grade, which you in Brisbane can see as the solar panel on houses and commercial buildings. That is a lot of talk about in the news and media for the moment, I've seen. Solar grade silicon is 99.9995 at least percent silicon, and this refinement has to be taken in the second step, so it's more than 50%. And natural refinement of quartz is important, so that's something I'm going to talk a little bit about, how to look into how nature by itself refines quartz quality, quartz purity by anatomical processes. So, metallurgical grade quartz is, as most industrial minerals, you can produce different qualities. So by knowing the properties of your deposit, you can mine selectively, you can mine and produce different qualities of quartz regarding related to purity, related to size, and of course you need to take care of customer requirements. Different customers has different requirements to the sizing and to the purity. Impurities are mainly related to aluminum, titanium, calcite, calcium, iron, boron, and phosphorus. Most of the elements that comes as impurities can be refined during this metallurgical process, but these elements are hard to refine, so they need to be low naturally in the goods. This is a furnace. This used to be the world's largest silicon furnace. Now they're currently building one that is a little bit larger, but this is a three-phase submerged electrode furnace with at least 42 megawatt capacity. The quartz is charged into this furnace from the top, together with carbonate material. materials, which is coal, coke, or charcoal, and also some wood chips. The wood chips is just there for keeping porosity, because this process will create a lot of gas that needs to flow through the charge, and wood chips just open up. The quartz will, on the other hand, contribute. If it's not good quality, it will contribute to block this gas movement by decapitating and producing fines inside the furnace that clogs every porosity of the material. So that's what thermal properties of quartz is for. Products from this process is, of course, silicon, but also microsilica, which is silica dust that is precipitated from oil furnace, and then also thermal energy, which is recovered from. So we need to study in situ properties, how the purity, how the thermal properties of the quartz is in situ, so we can take care of that when we mine it. And then also how they respond to crushing and screening and transport. All they do about with these quartz is just crushing and screening conversion. So this storage pile consists of quartz which is 30 to 100 millimeters. So that's all we want to ship it and maintain it during bulk transport from Europe somewhere or up to Norway or around Europe. So what we did was, one of the things we did was making cubes of quartz, cutting them to have same mass, same size. Shock heating this in induction furnaces, 10 minutes at 1300 degrees. This is how the quartz goes up. There's no mechanical treatment of this, it's just natural reaction to, and you see there's a difference between this hydrothermal quartz, which fractures a lot, and this is quartzite that doesn't fracture. So this is important just to observe how different types of quartz respond to heat, and then look at how that will be in a furnace where you need to have porosity. This happens to the quartz immediately after entering the furnace. It will clog the permeability and porosity. So we looked into these products from the shock heating even further. So we moved to the microscope, made thin sections, and impregnated the material with fluorescent epoxy or resin that we could use in the UV lab to see fluorescence where you have this, to study how microcracks in the material is developed. So this one is the original rock. So we are talking about this material. This is how it looks before being heated. Nice, pure, fine quartz grains, nice, simple grain boundaries. And if you look into it in fluorescent light, you see that you can see there is some space between grain boundaries. You see that epoxy resin has entered into the grain boundaries, but there is no internal damage in the grain. The grains are fine. After heating for 10 minutes at 1300 degrees, we see that in cross-polarized light, already you can see the difference. You can see that the grain boundaries are not that nice anymore. You see that the appearance of the quartz is a bit more dusty, dirty. And if you go into the UV light, fluorescent epoxy, and look at that, you see that grain boundaries has become more diffuse. You have some larger pores that occupies a lot of epoxy resin and makes the imaging process harder because they fluoresce a lot more. And internally in each grain you have small microcracks and also some inter-grain cracks across grain boundaries that the entire rock mass is fractured, which is showing that this is not just fractured a little bit. When you put this in, or when this moves down into the furnace, the fragments has weakened and will be grown into finer and more dusty grains on the way through the charge, which is 5, 6, 10 meters high, and create more fines as it moves down. We've also seen this as an indication of crystallite formation. So those of you that know the phase diagram for silica, you know that quartz is a natural ambient mineral. When you heat it up to different temperatures, you have transition to beta quartz and later to crystallite. And when you have formation of crystallite, which we'll look into afterwards, quartz expands about 15%. That's a significant expansion that contributes to this internal cracking deformation. So now this slide jumps a little bit away from quartz. This is an example from a limestone quarry, but it's just something we can use of course as well. Looking into microfractures again and how microfractures develop after blasting. So we see that this is a blast hole trace, and we have sampled along the profile away from the trace and see how microcracks are higher concentrated close to the blast than away from the blast. And this is in the middle between two blast hole traces. This can be used for to look into how the competence of the rock is when you're crushing and making the oxides. Maybe to plan blasting patterns. So a little bit looking into crystallite formation after heating. We heated quartz to different temperatures from 1250 to 1550 degrees. You see that crystallite in some of the quartz is actually up to 10% after 10 minutes and 15 minutes. This is significant and contributes when you know that crystallite is expanding dramatically. That contributes to weaken the thermal properties of the quartz. And this diagram is just removing this one and seeing how different all the samples responds, which is not that much. There is one sample that is more prone to crystallite forms, which is caused by our geological history of the quartz. So, and then natural refinement of quartz. This is from another deposit. It's a hydrothermal quartz deposit, which is very, very pure. It's one of the purest hydrothermal deposits now. It's intended for making very high purity silicon, but they need to know how to mine it in order to get the purest concentrate. The hydrothermal deposit is generated through several hydrothermal sequences. So we have in this picture is made by SEM cathode. So it's a CL image for those that know the CL. The bright quartz is the primary quartz, the first replacement of a hydrothermal deposit, and then the darker quartz is later hydrothermal events that has intruded the first quartz. The brightness of the quartz of the image represents the purity. So the CL is the CL signature of quartz is weaker if you have less purity because of the because of the rapid changes that happens when you have impurities incorporated. So we see that the bright one is the first generation, and we have not so dark one, which is the second generation, a little bit darker one, that is the third generation, and we have some very distinctive veining that's totally black, that's the fourth generation of course. And see how the impurity of the quartz is reduced by later events. This is confirmed with laser ablation SPMS, where we have, if you go back here, you see that this is still SAM-CL picture. You see bright quartz, dark quartz, and equivalent laser ablation analysis. You see that the content of the different elements drops when you enter into dark, late generation quartz. Same for both. This is a recent work done by one of my master students on this deposit. So that was quartz. Quartz has a wide range of use. Metallurgical grade and high purity quartz is maybe the most high-tech and those with the strictest requirements to purity and strength-wise. So we need to have mineralogical knowledge how to produce good concentrates of quartz with the correct properties. And we use different set of tools to test this mineralogy. And it needs to be done to allow for making different product qualities, plan mining operations, and blending strategies. So that was quartz. And now the last minutes will be on aggregates for concrete. I see that I have spent a lot of time, so I will do this quickly. Aggregates for concrete is important worldwide because there's a lot of concrete. There's a lot of problems related to aggregates in concrete because we have different deterioration of concrete based on cracking, leaching, alkali reactions, which has had a lot of focus the last few decades. Sulfate attack and carbonation. Sulfate attack has been known for a long time, but the problem with pyrrhotite in aggregates has been receiving a lot of focus the last 5-6 years because of something that happened in Canada, in Quebec, where they built a new housing area, and they used a specific aggregate for this. All the houses in this area, I think it was about 1,000 houses built for people, so domestic buildings. Formation of Aggregate, which has a complex formula and that varies. It's a result of oxidation of pyrrhotite. When pyrrhotite reacts with other material in the cement and form aggregate, it expands. Expansion is again a problem. And this is the foundation of a house that has total deterioration because of that. All the pyrrhotite spots in the aggregate resulted in this happening. So most of the 1,000 houses in this area have to be rebuilt. They have to change the entire foundation. And this has been seen also other places, but this area is a very, very good example of the problem. In Norway, we doesn't have anything like that problem, but there is a recent infrastructure project, tunnel, driven by TBM, so tunnel boring machine. They plan to use all the crushed rock from the tunnel to make concrete lining in top. However, somebody spotted some grains of pyrrhotite in those materials, so they had to discard all those thermal masses. Because they, according to the requirements, they couldn't use it. So the conclusion is that they was spent more than 200 million Norwegian kroners more, or about 30–40 million dollars, on buying aggregates from a nearby producer using. So economic loss is one thing, and also waste of resources is another thing. Rather than being able to use the masses produced from the tunnel, they have to buy the masses from a local supplier, because somebody saw a couple of grains of pyrrhotite and very strict regulations. And the regulations are, this is real European standards, saying that total sulfur content in aggregates for concrete cannot be higher than 1%. If you have indications of pyrrhotite, this limit drops to 0.1% in the and they don't say more about what's an indication of pyrrhotite. It's just an indication. So if somebody looked into a microscope and say, okay, you have no pyrrhotite, I saw one grain of pyrrhotite, then this is the So that's something we have been started working on now, to see what does that mean for different types of aggregates. What does it mean for producers? What does it mean for the concrete producer? And is the limits, are they realistic? Is that how they should be, or can they be modified to be a little bit higher? So that involves both geologists, mineralogists, and concrete experts of construction. So we will look into different methods to analyze both sulfur and sulfides. So this is a micrograph that I just made from the actual aggregate that we saw from Canada. I was planning to show you mineralogical, automated mineralogy, because we think that automated mineralogy would be the best way to actually say how much pyrrhotite you have. Unfortunately, I didn't manage to get good analysis before making this presentation, so I'll do that in another presentation, later stage. But we do have pyrite, and pyrrhotite in this. And not on this picture, but it is also magnetite in this one. So we started with our analysis. So this is the most recent project I started working on. So it doesn't have much data yet, but I'll just show you some things. We do see from XRD, X-ray diffraction, that we do have pyrite, we do have some pyrrhotite, and some magnetite. Pyrite didn't show up on XRD, probably because of it. Also, the levels of pyrite and pyrrhotite is below 1%. It can't be regarded as accurate levels, it's just an indication of the level. Because the nature of XRD is that if you have low contents, you're not precise the amount. So the total sulfide content is around 1% in this. This is just taken from different size fractions of this. We also tried differential thermal analysis of the same material to see if that could be more precise. This is a method that is recommended by the standards to use. Differential thermal analysis utilizes the temperature endothermic reactions, exothermic reactions that happens when pyrrhotite or sulfides are oxidized during heat. So you heat the samples to 700 degrees and measure the thermal response during heating. In literature, chalcopyrite has reactions at about 380 to 420 degrees, pyrite at 430, and pyrrhotite at 450. I also mentioned quartz because quartz is used, the alpha-beta transition quartz is used to check that the temperature readings. So we see that at 573 degrees we have the endothermic response from the phase transition quartz on both places. We also see we have from 340 degrees up to 540, we have a huge reaction for sulfides. However, we cannot from these reactions say if it's pyrrhotite, pyrite, or chocolate pyrite. So we can only say that there are sulfides in the world. And that's how they say it. Because you have two peaks, they interpret that you have pyrrhotite together with pyrite. If you had only pyrite, they say you only have one peak. You can't say exactly how much weight you have, even if you have two peaks. That's the indication of pyrrhotite we use today. To say if aggregate is accepted or not. And this is something we're going to work on in the future to see how we can classify or characterize these aggregates better with respect to or sulfides. The result of these analysis says that we have 3% sulfide and down to 2%, which is quite much higher than the 1% that the XLE returned. So it's a huge deviation between the two methods. So we're starting to work on this, and automated mineralogy will be one of the most important tools. So, for aggregates, the pyrrhotite problem is important, and we have started receiving funding from governmental bodies and industry to work on this and to find good solutions. I'm working together with a Canadian university that will be focusing on the effect of the sulfides and pyrrhotite in the concrete itself. So, process mineralogy is used in very different type of mineral resources. Industrial minerals are depending on detailed mineralogical knowledge to improve your yield or product qualities, whereas for construction materials, mineralogical knowledge in order to assess how the materials is applying to regulations and how the material will behave in the concrete support. And everything here is linked to the processes. As I started with, talking about process mineralogy, it's all about how the material works with the processes and can be optimized. So, any process or for any resource, processes may vary, so it's very different processes to assess. Thank you very much.